Um, this is number 3 on the non-calculator. Oh, you want 3 on non-calculator? I mean on calculator.
Did anyone get the number 2 right? Number 2 on the calculator portion?
Somebody did.
Okay.
For this one, for number 3, the decay of a certain radioactive element is, and this Y sub 0, remember, means initial amount. T is measured in years. What's the half-life of the element? And several of you asked me, how could you find that? And I said, if it was me, I would probably use algebra 2 to plug in some values. In other words, if I started with 2, maybe, that would leave me with 1. How long did it take me to cut in half? Solve it for T, right? Does that make sense? Or 1/2 equals e to the negative 1.2t, and now I just solve for e. So log both sides. The log of 1/2 equals negative 1.2t. This was calculator, so put this on your calculator and then divide by negative 1.2. And you should find that t is approximately 0.5776. And then for part B, how many years will it take for 98% of a sample of this element to decay? So I did the same thing. If I start with 1, whatever it is, it doesn't even say what the unit is, but if I start with 1, if 98% decays, then how much of 1 is left? 0.02. And now solve it. So divide by 1, which is still the same. So 0.02 equals, and take the log. And you should get approximately 3.26. Y'all did some funky stuff on those. Not sure what was going on. There were some derivatives and some integrals. I don't know.
Part B, I accidentally put in 0.98.
Yeah, you get
I did that the first time I did it. I put 0.98 and went, wait, that's not right. And I erased it. And I knew by the years, whenever I got the number of years.
Right, I didn't know what else to do.
Well, but based on my answer in part A, I knew. Right. Was your setup the same way? Did you do the same thing to solve it? Yeah, you used the half-life equation. I just used my algebra 2 now. Anything else? 5? Number 5. Non-calculated, yeah. The integral from 1 to e of 2 log x minus 6 log x. When I saw all these log x's, I immediately thought that's going to be my u. But in order to do this, if I just let log x be u, I would end up with 2u minus 6u squared over x. And I'm thinking, I don't know. So I split this into 2 fractions. Because that's one of my log properties that said, or one of my integral properties. And I'm going to pull this 2 out here. The log x over x dx minus, I'm going to pull this 6 out. Like 2 fractions.
Do we ever get partial credit?
I think so. There were 10 each, I think. There was only 10 questions. I let u for both of them be log x. And so I ended up with 2 times the integral from 1 to e of u du minus 6 times the integral from 1 to e of u squared du. You have to remember to change your bounds here, right? If you're going to keep them, otherwise you'll have to plug in later. So I did u of e, which would be the log of e, which is 1. So this becomes 1. And then u of 1, which is the log of 1, which is 0. So those bounds change, 0 to 1. So now I have 2 times, what is the antiderivative of u? 1/2 u squared, right, from 0 to 1, minus 6 times, what's the antiderivative of u squared? Can I do that? Yes. Yeah. So I get u squared, so I've got 1 squared minus 0 squared minus, this will become 2. One minus 2. Your what? What's the sign? Didn't split yours up, but you got it right. Two u minus 6u squared. Oh yeah, and then you did it. That's fine. So you did 2u du minus 6u squared du, and that's fine. You can do it like that.
Was number 7 the cube root of sine plus 1?
Number 7, cube root of sine x plus 125. All under the radical. Which other one did you say, Dylan? 6? Secant squared 3x minus 2 dx. So if I let u be the 3x minus 2, du is going to be 3 dx. Which means if I need a 3 here, I need a 1/3 outside. The antiderivative of secant squared is tangent. So you get 1/3 tangent. U is 3x minus 2 plus c. You want me to show you the bonus? You see something like this, your brain automatically should anyway go to some sort of identity. Mine started thinking when I first started this one, I thought, okay, I know that cosine squared x is the same thing as 1 minus sine squared x. Maybe I can use that somewhere because the derivative of cosine is negative sine, so maybe somewhere I can use. But anyway, what I ended up doing was I said, well, what did I do? Not plus. So now I could do cosine x times, I changed this. This is one you just had to play with to get. I can't give you a step-by-step on how to exactly do this. But cosine squared, I did go ahead and change to see what happened. 1 minus sine squared x squared. Now, if you let u be sine x, what is du? Cosine x. So what I have is the integral of 1 minus u squared, right? You agree with that? You FOIL this out. 1 minus 2u squared plus u to the fourth du. You can break this up just like y'all did on that number 3. So the integral of 1 du minus the integral of 2u squared du plus the integral of u to the fourth du. These are easy to take individually, and then you just have to plug back in. Remember that your u is signed. So this would be 1/2, nope, just u minus 2/3 u cubed plus 1/5 u to the fifth plus c. And what do we let? We let it be sine x. It wasn't a bonus because it was easy, y'all. It was a tough one. I didn't get it the first go round. The first go round, I put my 1 minus sine squared x in too early. I erased it and started over. It takes a bit. It takes a bit. That looks easier now because I figured out the pattern for you there and told you the 1 minus sine. But that was the hard part of it, was figuring that out. But this is how u substitution can be incredibly handy. But who'd have thunk we'd have to FOIL out a u substitution? All right, by the lines and curves. Oh, I see, because it's a quartic. One particle motion and then 2 area between curves. Let's see if we can do this. Let's see if we can find the intersection points first before we graph it. And first of all, right, you set them equal to each other. A quartic, remember what a quartic looks like, right? Both ends are going up if you think about in behavior because I've got a positive leading coefficient and an even degree. So it's going to look something like this. That's a quartic, right? And the quadratic looks something like this. This one is shifted up 4. I'm not sure what effect that's going to have on my graph. But let's see if we can find the intersection points first. Set them equal to each other. So x to the fourth minus 4x squared plus 4 equals x squared. Of course, make it equal 0. This is a quadratic form, which means what? I can factor it the same way I would a quadratic, right? X squared minus 4, x squared minus 1. Agree or disagree? Am I really smart? A lot smarter than me. Everybody goes to 0. What would your way be, Dylan? Not all this. I have 4 intersection points here, right? I would argue you might need a calculator to see the picture on this one. With this being a, well, I know it's intersecting -2, -1, 1, and 2. So I'm thinking this parabola is going to do something like this or something. Terrible rendition. Sorry. But it's going to, this is going to be closer together. I'm thinking something like this maybe, and this quadratic is going to come and do something like this. And so I'm looking at here, 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 and here. So the space between. Which the reason this one's hard is because the top and the bottom curve are flipping each time. Right? Do you see what I'm saying? For this first piece, the top is the x squared. Right? So it would be the integral from -2 to -1. And I got to subtract top minus bottom. So x squared minus, what's the bottom one? X to the 4th minus 4x squared plus 4. Yeah. Do y'all see that? Okay, so these are the points where it intersects, right? So it intersects at 4 different points. 1, 2, 3, 4. And I just started at the farthermost. You don't even have to be exact in your graph. You just have to kind of know what they look like. So I know I set each one of these equal to each other to find where they intersected. So this equal to this. Let me expand my picture here because I think this is where y'all are getting a bit confused. If it's something like this, I've got 3 shaded regions here, right? 1, 2, 3. And for each region, the function itself is shifting on which one's on top. So it's always top minus bottom, right? So here, remember the green is x squared, and the red one is my x to the 4th minus 4x squared. So to find that very first purple area, I'm going to do the green, which is x squared, minus the pink, but I need to know these bounds. Well, this is why I solved it, right? And I only need the x value. Well, if I know that my x is -2, +2, -1, +1, let me put them in order. That's the order they must happen when they intersect, right? This must be -2. This must be -1. This must be 1. This must be 2. Does that make sense on how I determine that? Yep. Yep. So to that, I'm going to add the integral from -1 to 1. This time, what's on top? X to the 4th minus. See, if you didn't have a picture, it would make this very difficult. Plus last integral 1 to 2. Which one's on top? X squared minus x to the 4th. The good thing is they're not very complicated. Once you have it, it's easy. It is. It's just a lot of tedious work, but I wouldn't even say that it's algebra 2 work past that when you're plugging in. It's a non-calculator problem. -2 to -1, so this would be -x to the 4th. What is that? Plus 5x squared minus 4. It is a lot of, this one is a lot of work. It's getting those bounds set up here. X to the -x to the 4th should be the same as the first. Antiderivative. Negative 1/5 x to the 5th plus 5/3 x cubed minus 4x. This one is going from -2 to -1. 1/5 x to the 5th minus 5/3 x cubed. This is, to me, I could do this all day long because I know this is easy. Right? I mean, it's a lot of tedious stuff, but it's nothing, there's no calculus involved past the antiderivative here. Leave it like what? You'd have to show it being plugged in.
Yeah, I would plug it in.
I have a question. When you combine x squared and negative 4x squared, how do you get 5x? I know I'm doing wrong.
Which one? The last
When
integral?
you're combining.
Here.
Yeah.
It's the same as the first.
I know. I'm talking about when you initialize.
Okay, so x squared minus negative 4x squared. So it's minus that negative. I like these. I think these are cool. I know y'all don't. But look at that graph with the little pieces in it. So cool. Okay. If I plug in -1, I get negative times a negative, which is a positive, minus, plus, minus. Now I got to put the 2 in. Thank you, Dylan. 2 to the 5th, 2, 4, 8, 16, 32. Right? Eight times 5. I think this is definitely becoming a calculator problem at this point. I feel like your book, a lot of the times, I would say, from this point, it should be a calculator problem. Most definitely. I have never seen you have to do this much by hand without a calculator on an AP exam. That is ridiculous. Now, the reason they're putting this non-calculator is they're wanting you to be able to visualize this. I have seen things like that where you have to do. You have to know what a quartic looks like. You have to know what a quadratic looks like and be able to identify those parts. And what I would say the non-calculator portion of this piece would probably be a multiple choice question, and it would say which of the following integrals represents the area between the two curves. Right. And if it's not, then it would be a calculator problem, and then it becomes infinitely easier. So the answer comes out to be 8. Use a calculator at that point. That's right. You're exactly right.
So couldn't you have just solved for one of them? If you know that, like if you have symmetry, I know that on some of them, don't you?
Yeah. There should double because these should both be symmetric. These pieces should have the same area, so it should be 2 times that first one.
Well, you're adding the integrals, but they're not.
No, they're not canceling. It should be. You should be able to say that 2 times this one is the same thing as adding this one because it's symmetric. You see what I'm saying? And then you just have 2 to do instead of 3. But yeah, you're right. All right, what else on your homework? Was that the hardest one? 3? Okay, so did I give you 3? Okay, so to do 3, the way you know right now, you would have to solve. You've got x equals y cubed. You'd have to make that y equals the cube root of x, which is the same thing, right? Everybody agree? Because I'm taking the integral with respect to x.
One fourth y squared. Solve for that one, and then solve for that would be 1/3 y.
You could. And so what you're doing is taking it with respect to y, which is what we're going to do today. But you're already doing it. So, but here's where you'd have to do the integral if you did it with respect to y. So these are the same things.
Yeah, I solved that one, and then
These are y values instead of x values. In this case, because it's 0, 0, and 1, 1, it doesn't make a difference. But you have to know that that's got to be the y values if you're doing y to the third minus y squared dy. Or I could do from 0 to 1, now these are x values. And I'm defining that here for you so that you see the difference, because these intersection points were 0, 0, and 1, 1. So my x and my y values were the same at each point. If this had been 1, 2, this one would go from 0 to 2. Because I'd have to take the y instead of the x, because I'm doing it with respect to y. Mm-hmm. This one would be, which one's on top? Cube root minus square root dx. And you should get the same answer either way you do that. Let me do it. You want me to do it with respect to y or with respect to x? Yes, I got 1/4 y to the 4th minus 1/3 y cubed, and I'm evaluating from.
oh no, I got the right answer. I'm just saying that I solved it.
And just to show you that it works out the same if you do it with x, because I'm extra. 1/3 x to the 1/3 would be 3/4 x to the 4/3, right? Minus a half plus 1 is 3/2, so that would be 2/3 x to the 3/2, and I'm going from 0 to 1. 3/4 minus 2/3. Which I hope is 1/12. Times 3, which would be 9, 12 minus times 4, 8, 12. Yeah, 0. I should get sharp.
So when you do 1/4 minus 1/3, it's negative 12. But yeah, negative. And then right? I subtracted 1/4 from 1/3. So 1/3 and then I got negative.
Yes. Because we're doing it with y, it's not top minus bottom, it's right minus left. So for y, we'd have to switch these around. We're going to talk about that today.
Well,
sorry. Yeah, that's fine.
I mean, I knew that area is negative, so I just put that to that.
Yes. Yes. Okay. Yeah. Can I go over what? 1? Find the area of the shaded region. So it looks like, first of all, I need to know those intersection points. It looks like those intersection points, if I let 1 equal cosine squared x, so I need to know where is cosine x 1, where is cosine x negative 1. So I'm at 0 and pi. Okay. From 0 to pi. I'm going to do top minus bottom, right? You should be able to. But do you know the antiderivative of sine squared x? Is it what? Okay, so let's think it through. Bless you, by the way. Do we know the antiderivative of sine squared x? And this was a non-calculator? You good, Aaliyah?
Yeah, like 1/2.
Did they do the square? I mean, the rectangle minus. They used the identity, didn't they?
I thought you could do it of 1 is not 1.
Alright, okay. Oh, we're on 17. Yeah. I think this is one of those antiderivatives that they're just assuming you know. Looks like they did a backwards chain rule kind of thing. Why isn't what?
Well, no, because they're different equations.
You're saying because it looks symmetric.
Why did they get
But if you work it out algebraically, it gives you 4 pi over 3. Interesting. I don't know because it does appear that way. I don't think the sine squared is perfectly symmetrical right there, and I could be wrong. But I'll look that one up and see. It looks like it there, but I'm not sure that it is. Yeah.
How do you go from 1/2 secant squared plus 4 sine squared to it's like they doubled it. I know they did, but how do you go from what I just said to secant squared plus 8 sine? And then
Lizzie, area is never negative. That's why. Area is never, so you can't take the negative of it. So what you could do here, sorry, my brain farted a second. I could actually do 2 times. Is this what they did, Noah? So yes, it's perfectly symmetrical. It's not going to be 0 because the area to the left of the y-axis is not negative. Yeah. Because that takes into account negative. This is area itself, and area is never negative. That's why we have to do top minus the bottom, and it takes into account all those negative derivatives. Yeah. But they did that because it is symmetrical. So if you ever have a symmetrical function, like if I just had x squared, sorry, right? And I wanted to know the area from -5 to 5 of x squared dx. Well, I could really, if I wanted to make my life a little bit easier, if one of those bounds is 0, whenever I plug in, I'm going to get 0, right? I could say, well, let's just take half of that area from 0 to 5 and double it. Because it's the same on either side, right? It's symmetrical. Now, you should get the same answer. If you didn't double it and do it, that's just a little time-saving trick. But if you did it this way, you should get the exact same answer.
I did that, and then I got secant squared plus 8 sine squared.
Okay, so you did you do from 0 or did you do from,
From 0 to
and you doubled it? The top one is 1/2 secant squared t. The bottom is -4 sine squared t. Right? I would split this into 2. 0 to pi over 3. This is another one of those identity ones. That's why.
Like then you're splitting it, NT plus 4T minus.
Which the antiderivative of secant squared is tangent. That's why.
I just want to check how you like split up with like in the back.
It is kind of. Let me get y'all a little sheet on the squared ones to help you with the integrals there. All right, let's take a little break really quick. All right, I will just go over this quick. This is a really, really easy concept. I don't think I'm going to throw volume in here today, although that was my plan. But best laid plans never seem to work for me in here. I don't understand. Doesn't matter what I plan in here. I'm not getting to everything. I never do. All right, area with respect to y. This is when the equation is in the form x equals blah, and you've got y in there. So instead of doing an integral with x's, I'm doing an integral with y's here, and I'll have a dy that I'm taking it to with respect to. The biggest problem here is knowing which curve to subtract from which one. So I'm going to show you 3 different scenarios, and these are in your book, but they're really good graphics, actually, and I don't like a lot of things in your book, but they're on page 406, but I'll draw them out for you, just so you see. If I have something that looks like this, and this is x equals g of y, and this is x equals f of y. If I want to find the area between these two, now remember, if I'm doing it with respect to y, that means my bounds here are y values. Okay, they're not x values anymore. So let's say I want to go from, I use C and D. I'm going to use A, B. I want to know what this area is. Okay, so I don't, this time my functions look a little bit different, but I'm going to go from A to B, lowest to highest. I start, whereas with respect to x, I do top minus bottom. Okay, when I'm with respect to y, I'm going to do right minus left. So this would be f of y minus g of y. So right minus. It's a little bit more confusing. That would be given to you. Find the area under the curve from whatever. What if it's not what? You may have to find the intersection points, just like before. These don't have intersection points, okay? So this would be something like if I had, if you think in terms of x, if I had y equals maybe sine x and then negative sine x or something. Well, no, that doesn't even work. Gosh, why can't I think? If this was just twisted the other way, and I said find the area from here to here, and gave you those numbers. This might also look like, this is the same, these are all referencing the same, this is B, and here's A. I should put A at the same point. Still the right curve minus the left curve. From A to B. If I told you to find from A to B. And this is A. A is still in the same place it was before. This time B is this intersection. You just get to look for the Y's instead of the X's. That's the only thing that makes it confusing. It's still, I'm sorry, yep. So this is still A to B, F of Y minus G. And of course they could intersect also, so it could look something like this. Let's call this XB. Let's call this XA. See if this makes more sense. This is the third scenario, yeah. This is F of Y, this is G of Y. So I'm still, this area is still from, this time I'm going, notice how I'm using the Y values instead of the X values. You're still setting them equal and finding where they intersect, but you're looking for the Y values instead of the X. It's going to be F of Y. I'll do one example with you, show you what I'm talking about. Let's do number 11. Let's do number, yeah. Is it with respect to Y? Oh, it's not with respect to Y. Let's do number 11. This is a calculator problem. Oh, no, that's not with respect. Stop. Don't do 11. There's not a lot of these that are with respect to. We'll still do it. We'll still do it. Yeah. I'm going to solve it for X so that I solve it with respect to Y instead of with respect to X. So I'm going to move the 1. So I have Y squared minus 1 equals X. Agree or disagree? Okay. Say that again, Lizzie. Oh, I got you. Yeah. Yes. And you just had to do the right minus the left. All right. I need to figure out which one goes where. I need the intersection points, right? So I need to figure out what these look like. Any ideas? So, and how are you figuring that out? Just square root. That's exactly what I would do. I would just square root here, or you can think a parabola on its side because the y is squared instead of the x. I tend to think about this if I did solve it for y, it would be a square root graph, right? One going up and one going down. But Aaliyah is absolutely correct. This is a half of a square root graph. I mean, a parabola graph going up. This is, but on its side, right? So something like this one's going to be something like this. This one is down, so it's going to be something like this. And what does it say? Does it have two? What's it look like if you graph it? Who's got a calculator? graph the square root of x plus 1, and then graph the square root of 3 minus x squared. See what the 3 minus x. You're right. That's why this is a calculator problem too. All right. So it looks more like this. So this is the area that I'm looking for. No. So in this case, the intersection point is not really doing me a lot of good, right? Because the intersection point is here. So I need to know the curve on top minus the curve on bottom, right? So if you, and since this is a calculator problem, I would definitely be using my calculator to do this. You look pained, Josie. Okay. Why do they want this class first block? I don't know. They always do it first block too. Second's also longer, so it would be.
So do I need to find the intersection and 0?
Fine, look at your graph. Let me see your graph.
I mean, like the end of the scene. I mean, right out front, you deserve that. You look good. Okay, yeah, that was bad. But like, I don't know, it was like, and then like not even the audience. I mean, like, it wasn't. It's a little. Yeah, but that was a douche thing. Yeah. If somebody came up to me and held a gun to my head.
Welcome. All right, I do need the intersection point. I lied to you. I'm thinking in terms of x instead of in terms of y. So I need the lowest y goes, which is obviously what? 0, up to, and I need this intersection point. So use your calculator to calculate the intersection or set them equal to each other. Doesn't really matter. The y value is 1. And I'm going to do the right curve, which is 3 minus y squared, minus the left curve, which is y squared minus 1, dy. The y values, yes. So I'm going from 0 to 1. 3 minus negative 1 would be 4. Negative y squared minus y squared would be minus 2y squared. dy. You said no, the answer is like 7.542. Oh, it's not actually 1. Okay, so it's 1 point what? Y squared minus 1 equals 3 minus y squared. 2y squared equals 4. I'm going to just do that. So if I plug in the square root of 2, I get 4 minus 2 times the square root of 2 squared minus 4 minus 0. Oh, what am I doing? Stop, Stacy, stop. Somebody, I was about to say, somebody stop me.
Stop.
Stop. Antiderivative is exactly right. 4y minus 2/3 y cubed, evaluated from 0 to square root of 2. Now,
How'd you go from that to that?
antiderivative.
No, I'm talking about 3 minus.
No, 3, this is subtraction. You're overthinking it. 3 minus negative 1 is 4. Negative y squared minus y squared is negative 2y squared. And now plug in, I don't need to worry about the 0 because 0 is going to be 0. Square root of 2, so I got 4 root 2 minus 2/3 times the square root of 2 cubed. If I am Dylan, I leave that just like that. I don't think so, not whenever it's minus 0. Like, not whenever it's 0, no. That's, no. As long as you're showing this part. You see what I'm saying? All right, let me tell you what I want you to do for homework. We already did 3, so we'll do 4. Those are all those. Pick up the calculator. The hard ones were the ones before with the non-calculator. Wait. I would rather do 21 through 33 threes and then pick up, so 21, 24, 27, 30, and then 33. And then pick up 35. That's good. And a random particle motion.
They do nothing for like the first hour. They stand around and talk to each other. I swear. While we were over there taking pictures, like for me today, they were all just sitting there. All three doing nothing. It's like 5.
But they don't do. But they're not.
This is my fear. You guys, every like we go to every different school, ask their baseball team, are y'all good at baseball?
That's every team everywhere of any sport.
Soccer team last year, we all.
We're sleeping on the table. Anytime we go over.
Are they, or like, is
I mean,
that just what they
probably
say?
not. No, we're sleeping on the table. We definitely are.
They'll sleep on the side.
Okay.
They're sleeping on the golf team, though. Last year.
You'll say that every year.
No, last year we knew.
So I would probably.
This year we have Dan back and Rex who were playing. We have Mormon. Yale.
Yale. Oh, well, you know, I have to.
Every game. Dude, I think, are we going to decide winner? There was that, like, was it sinkhole?
It's like tired.
Oh, I forgot.